This is the EdExcel AS Level Maths Paper 2 from the 2023 series, and this paper covers the mechanics section. Question number 1. Two children, Pat and Sam, run a race along a straight horizontal track. Both children start from rest at the same time and cross the finish line at the same time. In a model of the motion, Pat accelerates at a constant rate from rest for 5 seconds until reaching a speed of 4 meters per second, and then maintains a constant speed of 4 meters per second until crossing the finish line. Sam accelerates at a constant rate of 1 meters per second squared from rest until reaching a speed of x meters per second, and then maintains a constant speed of x meters per second until crossing the finish line. Both children take 27.5 seconds to complete the race. The velocity time graph, shown in figure 1, describes the model of the motion of each child from the instant they start to the instant they cross the finish line together. And that's what we can see in figure 1 here. Part A, using the model, we have to explain why the areas under the two graphs are equal. The areas represent the displacements of the children. Since they both run the same race, their displacements are the same, which is why the areas are the same. Part B, we have to find the acceleration of Pat during the first 5 seconds. If we take a look at the information given for Pat, we see that Pat accelerates at a constant rate from rest for 5 seconds until reaching a speed of 4 meters per second. So, because we have constant acceleration, we have to use the Suvat formulas. We will be using v equals u plus at. So, using v equals u plus at, we know that the value of v is 4, and this is equal to u, which is 0, plus a, which is what we're finding, multiplied by t, which is 5. So 4 equals 5a, in which case we can conclude a is equal to 0.8 meters per second squared. Part C, find in meters the length of the race. If we consider the motion for Pat, we can find the area of this trapezium, and we can do that by finding the area of this triangle and adding that to the area of this rectangle. So, for part C, the length of the race then, we have 1/2 times by 5 times by 4, and that is the area of this triangle. We have 1/2 times by the base times by the height, and then for the rectangle we have 4 multiplied by the difference between 27.5 and 5, which is 22.5. So we multiply 4 by 22.5, and if we work this out, it turns out we get 100 meters. Part D, find the value of x, giving your answer to 3 significant figures. We are required to find this value of x. Now, if I consider the line shown here, we know that this line has a gradient of 1. In a velocity time graph, the gradient represents the acceleration, and we know that the acceleration is 1 meters per second squared. So, if the gradient is 1 of this line, you can think of the gradient to be change in y over the change in x. So the change in y is the same as the change in x for us to have a gradient of 1, which means we have the value of x here. And for us to find the value of x, we need to recognize that we have the same distance under both graphs. So we can find the area of the trapezium as it relates to Sam. So we have a half times by x, so we have a half x squared. That is the triangle here. And then we add on to this x, which is the height, multiplied by the length, and the length is the difference between 27.5 and x. So we multiply x by 27.5, subtract x, and this is equal to the same length that we have for part, which is 100. So if I multiply by 2, we have x squared plus 2 multiplied by x times 27.5 subtract x, and this is equal to 200. So expanding and simplifying, we have x squared plus 55x subtract 2x squared subtract 200 equals 0, in which case we see x squared subtract 55x plus 200 is equal to 0. And if we attempt to solve this equation, if we use our calculator, we have a polynomial of degree 2. We have 1 x squared subtract 55x plus 200. So we get a value of 51.0 etc. and 3.9 etc. So we have x equals 3.92 and 51.1. And if we think about which value of x we require, well, this x is below this 4, which means x needs to be less than 4. So x will equal the 3.92 only, and that's because x is less than 4. So the value of x is 3.92 to 3 significant figures. Question number 2. A small stone is projected vertically upwards with a speed 39.2 meters per second from a point O. The stone is modelled as a particle moving freely under gravity from when it is projected until it hits the ground 10 seconds later. Using the model for part A, we have to find the height of O above the ground. So for part A, we begin with a diagram. We've got the point O, and we've got the ball which is projected until it hits the ground. What we need to find is the distance from the ground to O. And we can do that using the Suva equation S equals ut plus a half at squared. So if we use S equals ut plus a half at squared, we are finding S. So S is equal to, now here, we've got the initial speed 39.2, we've got motion due to gravity, which is 9.8 meters per second squared, and then we've got the time, 10 seconds. So S is equal to 39.2, which is u, multiplied by 10. Subtract, because I'm taking upwards as positive, which means when it's going down, gravity is negative 9.8, which is why I've got the negative. Then I've got the half times the 9.8 multiplied by the 10 squared. So it turns out we get negative 98. So the displacement is negative 98, which means then O is 98 meters above the ground. Part B, find the total length of time for which the speed of the stone is less than or equal to 24.5 meters per second. So there's two possible scenarios. One scenario is we have V being 24.5, that's when it's going upwards, or we've got the other scenario where V is equal to negative 24.5, that's when it's going downwards. And for us to find the time, well, I know what V is, I know what the initial speed is, that's 39.2. I know what the acceleration is, that's negative 9.8 meters per second squared, and I'm finding t. So, using v equals u plus at, if I think about the v equals 24.5 to begin with, I've got 24.5 equals 39.2 subtract 9.8t, and if I solve for t, you will find t to equal 1.5. And if I think about the v equals negative 24.5, I've got negative 24.5 equals 39.2 subtract 9.8t, which means t is equal to 6.5. So the range of times, delta t, that's equal to 6.5 subtract the 1.5, so we have 5 seconds. Part C, we have to state one refinement that could be made to the model that would make your answer to Part A more accurate. For Part C, we could include the effects of wind and rotation to make our answer more accurate. Question number 3. A fixed point O lies on a straight line. A particle P moves along the straight line such that at time t seconds, where t is greater than or equal to 0, after passing through O, the velocity of P, v meters per second, is modelled as v equals 15 subtract t squared subtract 2t. Part A, we have to verify that P comes to instantaneous rest when t equals 3. So for Part A, when t equals 3, we have v equals 15 subtract 3 squared subtract 2 times by 3, and if I work this out, 15 subtract 9 subtract 6 is indeed 0, which means P comes to instantaneous rest when t is equal to 3. For Part B, we have to find the magnitude of the acceleration of P when t is equal to 3. So, we know that v equals 15 subtract t squared subtract 2t, and the acceleration is given by dv over dt, and if I differentiate v, we end up with negative 2t subtract 2. So, when t equals 3, a, which is equal to dv over dt, that's equal to negative 2 times 3 subtract 2, which is negative 8, which means the magnitude of the acceleration is 8 meters per second squared. Part C, we have to find the total distance travelled by P in the interval 0, which is less than or equal to t, which is less than or equal to 4. At this point, it's a good idea to sketch the graph of v against t. So, if I sketch the graph, we've got the graph of v against t, and at t equals 3, the velocity v is equal to 0. And we've got two portions here. We've got the portion above the t-axis and the portion below the t-axis. So, for us to find out the total distance, what we have to do is integrate from 0 to 3 and add on to that the integral from 3 to 4, but bearing in mind here would have a negative area because we're below the t-axis, which means we are required to find the magnitude of the integral from 3 to 4 of v with respect to t. So r is equal to the integral of v with respect to t. So we have the integral of 15 subtract t squared subtract 2t from 0 to 3, and then we add on to this the magnitude of the integral of 15 subtract t squared subtract 2t from 3 to 4. So if I work out what each of these are, well, integrating 15 subtract t squared subtract 2t, I end up with 15t subtract t cubed over 3 subtract t squared, and I'm evaluating this from 0 to 3. And I add on to this the magnitude of the integral of 15 subtract t squared subtract 2t, which is 15t subtract t cubed over 3 subtract t squared, which is being evaluated from 3 to 4. So if I substitute in t equals 3, I have 15 times 3 subtract 3 cubed over 3 subtract 3 squared, which is 27. So for the value here, well, if I substitute in t equals 4, I have 15 times 4, subtract 4 cubed over 3, subtract 4 squared, and then I need to subtract the result when I substitute in 3, and when I substitute in 3 I get 27, so I get negative 13 over 3. So I need to add on the magnitude of negative 13 over 3. So I would have 13 over 3 being added to 27, and it turns out we get 94 over 3 meters. And as a decimal, we have 31.3 meters to 3 significant figures. Question number 4. A car of mass 1200 kilograms is towing a trailer of mass 400 kilograms along a straight horizontal road using a tow rope as shown in figure 2. The rope is horizontal and parallel to the direction of motion of the car. The resistance to motion of the car is modelled as a constant force of magnitude 2R newtons. The resistance to motion of the trailer is modelled as a constant force of magnitude R newtons. The rope is modelled as being light and inextensible. The acceleration of the car is modelled as a meters per second squared. The driving force of the engine of the car is 7,400 newtons, and the tension in the tow rope is 2,400 newtons. Before we do anything else, let's add all this information to the diagram. So we've got the mass of the car, 1200 kilograms, the mass of the trailer, 400 kilograms. We've got the resistance of the car, 2R newtons, the resistance of the trailer, R newtons, the driving force of the car, 7,400 newtons, and the tension in the tow being 2,400 newtons. Using the model for part A, we have to find the value of A. Now for us to find the value of A, we need to use the sum of the forces equals mass times by acceleration. And what we can do is consider the entire system. So if I consider the entire system, going forward I've got the 7,400, opposing it is the 2R, and I've also got this R which opposes it. So this is the sum of the forces, and this is equal to the mass. So for the mass I need to add together the 400 and the 1200, and I multiply this by A. So if I tidy this up, I have 7,400 subtract 3R equals 1,600 A. Let's now consider the trailer. If I consider the trailer going forward, I've got this 2,400, and opposing it I've got this R, and this is equal to 400 multiplied by A. I'll call this equation 2. Now I need to find out what A is, so I need to solve these simultaneously. Now let's get the R's the same by multiplying 2 by 3. So 2,400 times 3 is 7,200, negative R times 3 is negative 3R, 400A times 3 is 1,200A. Let's call this equation 3. So I've got equation 1 and equation 3, and if I do 1 subtract 3, I can eliminate the R's. So 7,400 take away 7,200, that's 200, and 1,600A subtract 1,200A, that's 400A, and if I solve for A is equal to 0.5 meters per second squared. So in a refined model, the rope is modelled as having mass. So this time we're including the mass of the rope, and the acceleration of the car is found to be A1 meters per second squared. For part B, we have to state how the value of A1 compares with the value of A. So if we are including the mass, then we can say an increased mass for the same force reduces the acceleration, which means A1 is less than A. We now have to state one limitation of the model used for the resistance to motion of the car. So for part C, the resistance is modelled as a constant, but actually it is likely to change with velocity. So resistance is no longer constant.